Hello, let's start coding. We will be coding exactly what. First of all, we're gonna just define constants or x, y, and z coordinate of a particle and make it to move. But for starts, we're gonna just make first of all plot. Start it. Code CLC close all. So first of all, we need to define one particle. We're gonna talk about one particle. We're gonna give its x, y, and z coordinate. X is equal to, let's say, 0 into coordinates, y is equal to 0, z is equal to 0. This is the coordinate, but we had also have a unit time it will be going, or you can go for 1 second also as you wish. 0 to 10 as going 1 units up, 0 1 10. Okay, 0 1 2 3 4 19. Yeah, like this, changing the range like a range, or you can use linspace or whatever. So x is equal to 0, x so let's say this is the initial condition, particle is at the origin, and we need to plot this thing. Plot 3 for 3D plot x comma y comma z, and we're gonna show it as like 0 on a circle, like a circle. You say O and run it. It will be showing this plot xyz plot, and x, y, and z with this thing at 0. Let's show the grids. Let's create grid on. Okay, now it's good. It's at 0 0 0. Look at the limits from -1 to 1, -1 to 1. So we have to change the limits. Let's change the limits of it. In order to change the limit, you can do it like set function. There's a function set, and G says like current active plot. You're gonna go for z limit. I'm gonna mention it as like -1. Once it's already -1. Okay, so 0 to 1, 0 to 1. Same thing. While limit, you're gonna go for 0 to 10, and z limit, x limit. Note of the x-axis that can be seen. 0 to 10, run it. Okay, now you can see it from 0, x range. This is x, y, and z. 0 to 1. Okay, now today we are gonna talk about like how to move this particle. This is this particle, the point. You have to move this particle from this point to this in along x-axis. How can we do that thing? Okay, yeah, we have to animate also. As it goes on, it has to animate. You have to use some loops so that you can animate it. Like you can show it like that. Okay, we can name this as a variable h. And plot it. Okay, let's go. Okay, this is it. Okay, this is one thing else. Like when you apply set function, it will be a recent plot, most recent plot. It can't just be on any plot. You can give, you can't just give it on any plot in consequence for class line. Okay, like that. Get on GCA. Yep. T2 x2 is not T2. Second position, different changing. Okay, so we have to go for loop for I is equal to look, for t0 we already had mentioned xyz. For t0 xyz has also mentioned, so we have to change, start from the 2 second state to length of t. So like 0 has already been talked about, so data goes 0 0.1 0.2 like that. We're talking about every time as it changes. So length, like how many times we're gonna go it. So time will be changing accordingly. The you can use indexing. Okay, so x would be like this. X, since x is a function of t, ut will be 1. so it would directly proportional to Ti. So it's directly from y would be constant 0, we're not changing along y-axis, z also we're not changing along z-axis, the motion of the particle. Then we need to update the plot. Which plot we have to update? H, and we're only updating the x data, and the x data would be x, and let's see what will happen. Okay, it's here, but it's like too fast, you can't even see it. Oh my god, I can't even see it. So what if I do pause? Yeah, now you can see it's moving, but frames are like frame drop is there. Not smoothly, there is something going on. Okay, there's another function to just improve the frame drop. Use like this for x actually along x-axis. We're not updating the x, y, and z because at the final move out, but at the any other position we don't know the positions of this particle at other time. So you can actually change that thing by going like xi. So at every state it will be saved. But yeah, I have to change here xi indexing. Yeah. So every time t it will be saved. Time t will be saved. Okay, it's very small. Anyway, these are all the states at different times. X states, Y states, and Z states. You can see here type, double. Okay, or you can actually store this thing. Okay, but in programming you always go for like unit time, 1 second, or whatever unit time is, and save it like that. You run it for unit time. Anyhow, okay, you can also save the animation. For every plot you have to save the you have to save every frame. So there's a function to save every frame. First of all, create a variable m, name it 1. Create a movie. Is there any function? Movie. Yeah, there's a function. Just name it frame. Yep. Frame of m is equal to get. Every frame will be saved. Every plot will be saved. Get frame. Like that. At frame m, indexing m, it will be saved at frame. So every this one m is equal to, we have to just change the indexing, increase the indexing by 1, and frame m get, I think it's same like that. Frame, let's see, this timing is so slow. Yep, I need to see the structure of frame. Yeah, it's saved like this. You can save it as a video file. Yep. In video file you need to first of all create an object. I think it's video, yeah, video writer video, something like that, and you're gonna name it video.avi. That's a video format. Okay, yeah, I have to create, I already have created frames. So first of all you need, right now there is something called as video write video. Yep, write video, we will be writing v object, and the thing will be writing frame. Run it. Let's see. Okay, write video object must be, okay, it should be open. So you have to go for open this object v. Okay, yeah, it's saved here. You can see it's here saved. This way you can actually save your animations. So now we will play. Okay, it won't be deleted this time. Just comment it. Okay, We will play with this code. We have will get apply some motions on y-axis and z-axis also. Nice. So in y-axis we can also give the same thing like independent upon time t of I. Wait a second. Okay, I forgot something. So you have to update this y data here also. Y data. Update y will update everything. Z data. Z I. Z I. Okay, yes, now it's moving along y-axis also. Okay, now let's give some other motion to it. It's like a mass. Like this is simple point, doesn't have any dimensions. We're not actually talking about particles here. This motion of a point in different directions. It's like this. You can make a function, nice function. Don't have to write this much in this main function, main code. Okay, let's do one thing. It's like, yeah, we have to remember one thing about this thing, that this velocity is constant here. That is the main topic we have talked about. Okay, here talk about one thing. When we talk about constant motions, u with time, u is constant with time. So distance is equal to u into time t. There is no acceleration, it will be constant. So u will always be whatever the initial was, u into time t. It's constant. We are keeping it here as 1 meter per second. Anything, any unit. Okay. Now let's give sine in the direction like sine function. So it will be like, okay, now you, in order to just define sine, you can go with sine of t, but it will be better to actually give it some time period to it, like a particular time period will mean maximum. So at, let's say time t is not 5 seconds or whatever, 5 units, it will mean maximum. So the function would be sine of, at t it should be maximum, so you can go for 2 into pi into t divided by t. When it will be 5, 2 pi is from sine of 2 pi is equal to 0, so it will be like, it will not maximum, like it will just be at its initial state, but t should be actually t1. This is the initial one. Yep, 2 pi at t1, this is the same thing. So initial states will be like the function defined state. Here we're going to go ti. Let's play it out. Yo. Okay, this limit is right, wrong limit. Wait a second. Okay, that limit we have to change because it's not seen. -1 to 1, the maximum will be. Yep, now it's good. Okay, it's actually moving on y-axis, that's why it's looked like that. Keep it 0. Now you can see. Now it's nice. At 0 you can go for cos, anything, cos motion. Okay, y is actually 0. Y is not changing. So this is okay. We have to go for now. Second particle. Now define second particles in the same plot. In order to do that thing, we just define second particles in matrix form. Let's keep 0, 0, 0 sine. Let's keep it at, it will be like distinct, having distinct motion, not the same as particle 1, different. So in here you have to go for ti and just go give it a simple motion. This one only in x direction, particle 2, that is independent of the first particle, not connected by anyhow. It's moving in x, particle 2 is moving in x direction. Okay, let's see if it will work. I throw comma. No, I'm just, it's the column is just changing, not the rows are not changing. It's okay, wait a second, xi. Something I did wrong, something xi. I actually don't save it. Xi, ti. Okay, ti is actually the same thing, that doesn't matter. Let's see. Yep. Okay, 0, 0 is going along, x-axis 0, 0, 0. Okay, because I was saying indexing it wrong. This particle 1, this particle 2. Yep, and at the same point. There and so if I have to save it like indexing, I would say I have to save the state at every time. Wait, x, where is x? 10, 10. Okay, I would save ithrow comma all column. Ithrow comma all column, but I have to change the ithrow. Okay, let's see if it will work. I comma all column. Control C, Control Yep, it's saving. You can save the state as well. Yep, every state is saved. And you can actually add the particle as just number of. Now you can add matrix, another element to it, to add another particle. So we can give any other motion to this. This time we're going to give you particle 2 motion y-axis. Okay, y-axis. So we have to actually change the limit as -1 to 1. I'm gonna give it sine. Okay, let's give it same motion, same function, sine dt. In here I'm gonna give it, let's see, yep, let's see how it will go. Oh yeah, going to particle. Okay, it's like when you go for particle, actually animate or particle, then they will collide, then they will behave, interact with each other, forces will be there, collision will be there, there will be different scenarios. You can code it accordingly. Okay, so this is good. Okay, wait, it's better to make one simple function, generalized function for everything we have just done so far. Okay, we create a function that will initialize their plot, 3D plot, and we will be calling it initialize, and we will be giving it a dimensions, number of particles, n, and initial state board. What is happening? Okay, initial state x, initial boundary condition or initial state of the particle x, y, z, and we're going to define h as plot of plot 3 x comma y comma z comma shown as like O. How it will be shown? Initialize number of this x, y, z. Okay, if n is like, okay, I will show you one thing. Save it. Initialize function. Okay, if we define a function second, and we just call n is equal to 1 only, and we define h is equal to initialize, and we just give it n. Don't give it anything, because for n1 it just keep it like default, like 0, 0, 0 state, but it won't work. It needs not enough input arguments. It always wants some argument to it. But if default is like 0, 0, 0, x is equal to 0, y is equal to 0, not equal to 0. So you are already going to start from a default state. So you will define a function like this if number of arguments is greater than 1. So I don't really have to always mention x, y, z. Okay, understood. Number of arguments is equal to greater than 1. Let's say it is going to, for time to keep it plot 3. Okay, keep it the same thing. And just don't go for logic this time, just run it. It will work. Now it's not enough input arguments. Wait a second. Okay, wait. Okay, I have to give it. It is greater than 0. Okay, it has blocked x, y. Okay, I understood. Okay, x is equal to 0. I have to give initial state. Y is equal to initial state, and z is equal to initial state. Okay, this time it did work. Actually, it did work. Okay, so what I was saying, you will like it will work if this was not given. Let's see if it will work. Yeah, it did work. I don't think this has any meaning to it. This has no meaning to it. If I mention it, yep. Okay, x is equal to 0. Okay, control T if n is equal to 0 or n is greater than, you can mention number of arguments is greater than 0 or n is greater than 1 or number of arguments is greater than 1. So you are going to mention x in that time for every other, like x, two particles, there were two x's. So for 2 indexing of 2, I is equal to 1 to length of n. For 2 it will be like 2 times xi is equal to, mention it. Oh, yep. Wait a second, x is already there. I don't need to mention it for x actually, because I'm putting x as 1. Okay, yep, you can do like this. If it is greater than 1, if it is actually equivalent to 1, equivalent to 1, then you can put it like there. If it's not, then whatever is x, y, z is x, y, z. Let's see if it will work. Yeah, it did work. Okay, we'll keep grid on. So if n is equal to 1, only one argument given, then it will be saved like this, this, and this. If it's not 1, I'm going to give it. Okay, it doesn't matter. Give it. What if it is only 1, 2, and 3? Initial state. It will work. No, it don't work. That's great. X, Y, Z. Not enough input arguments. Initialize X, Y, Z. Not enough input arguments. Two and 3. It's working. What was he saying? Not enough. Okay, I was just running maybe this thing. Yep. Okay, it also works. 1, 2, and 3. Nice. Whatever it will give, it will be here. Yep. If it's two particles, 0, 1, 0, 1, 0, 1. Yeah, one is here, second is here. Good. So we're gonna use grid on is already there. Just set these limits accordingly. Set GCA for our limits. Okay, one is there, one is here. Okay, problem with that one. 0, 10. Nice. So we just made a function called initialize that will initialize this whole code from. What am I initializing? I'm just initializing a plot so it can be used later on. Okay, it's like state, some state. Why have I mentioned an if n is not 1? Don't even mention. Yep, I was going for NAS. It will also work. If n is not 2, then it will go for that thing. Grid on. Okay, this is okay.